Now, our next speaker is Dr. James Barnard, who is the 2007 Clarke Prize laureate. He is widely known as the father for biological nutrient removal, and he has had a very significant impact in preventing eutrophication of valuable water resources. And for that, he also won the highly prestigious Lee Kuan Yew Prize from Singapore. And today he's going to tell us about how aerobic granular sludge can be used towards biological nutrient removal. So please help me welcome Dr. Barnard.
Well, thank you very much, and thank you for the honor of being asked to talk here today. I was just listening to Professor McCarty, and it reminded me of Flip Wilson, the comedian from way back, and he was talking about the church of what's happening now. He said because the Reverend Leroy didn't talk about what happened yesterday or what's going to happen tomorrow, but what's happening now. So right now I think I would like to tell you a little bit about the technology of using the granular egg. Whoops, sorry. Problem of being tall. I couldn't see the screen. So what I'd like to just talk a little bit about the earlier observations of granular sludge and what it really is, the selection processes and the development of at Delft University, and the advantages and some observations and some of the pilot plant work that we have done on that. Now, the activated sludge process was discovered about 101 years ago, and at that time they irrigated. In fact, they were right there where Professor McCarty was. The main interest was to get that nutrients on land, and in fact their work was funded by the grocery organization or something like that, because they wanted to just treat the wastewater in such a way that you can use it for irrigation. And so they were aerating the wastewater just to make it fresh, so they irrigated, but it just went back to being rotting again. And so they get the idea to keep some of that sludge in the system and decant it. And what they decanted was not only the liquid, but they also decanted anything that wouldn't settle. So it was a selection process. So what they did then is they had a batch reactor, and they filled up the reactor, and then they aerated it, let it settle, decant, and then the secret then was that they put all the wastewater in at one stage. That gives you a very high F to M ratio. And even then, in their work that they've done in 1914, they noted that they were seeing granular activated sludge. They didn't understand it, and 90 years nothing happened until we started seeing research in this field. Now, I don't have to mention that activated sludge processes, the conventional activated sludge processes in which we have anaerobic, anoxic, aerobic zones, has been with us for some time now. And this plant here, for instance, produces total nitrogen of 1.8 milligram per liter over a period of 5 years. But it is complex, and what we are seeing is that with a granular sludge we can actually basically do it all in one. And what really attracted me to it is that I've actually experienced it myself, and this is an example here of the pilot plant that I start, or the laboratory scale work that I start when I started looking at nutrient removal. I started where somebody had actually done work before. My friend Balakrishnan at the University of Texas was working on a system in which he had a contact stabilization process, and in the contact stabilization process, I set it up here. He would have high rate treatment, and then he would have a nitrification stage, and from the nitrification stage recycle it back to the stabilization zone where he switched off air, and he got 85% denitrification. And but when I set up the contact stabilization plant, I didn't waste any sludge. I just let it operate and let it run. anticipating that I'm going to put the nitrified effluent back in there. And what I found is that I described it at the time that the activated sludge looked like coarse sand, and it was actually granular sludge that I produced. And the mixed liquor solids was 16,000 milligrams per liter, and in the contact and in a stabilization zone, I was going up to about 24,000 milligram per liter, or 2.4%. So I was always wondering about that observation there, but here another observation is we had to build this plant really on a postage stamp. This is for Dublin, and this is about a 180 MGD plant, and we had to build it on this very, very tight site. And it was basically specified that we should use SBR, and there was a story that SBRs don't bulk. But I think the reason why that story developed is exactly because in the lab or in the pilot plant like Arden and Lockett used, you take all this wastewater and put it out in one go, so you get a very high F to M ratio. But if you have an SBR and you have to feed it during the aeration cycle continuously, it's a different story. And so I was very worried about bulking in this plant, and sure enough, we had to get an SBI of less than 100 to get the flow through the plant, and by the time we started up, the SBI was going up to 180, and so we had no option other than try feed during the decant phase. So here we were decanting and then feeding into the sludge blanket here, because that is not aerated at the time. So where you feed it, there you have to have a very high F to M ratio. And what we found is that the SBI dropped to 50 milliliters per gram within days. And it made the operation so much simpler. And just to give you some idea of the size, that ring there would encircle a football field. And then the other advantage, of course, with the SBRs, we could stack it. So what you see here is in meters that was 7 meters deep, and we had two tanks, one on top of the other, and we could put the supports through the bottom tank because there's hardly any moving parts in there. Also, and this is quite recently actually, we had a small treatment plant up in Washington State, and we were having very strong waste coming in a small anaerobic zone, and we were actually producing granular sludge. So it just develops. You don't really have to work at it. And in this case, the SVI went down to about 20 milliliters per gram. And one of the reasons was we were wasting surface from the surface. We didn't waste the RAS. We wasted from the surface, and so we kept wasting the lighter sludge. And again, it's just a selection process that gets us there. So this was just a picture of it, that sludge on the microscope. Now, granular sludge, and I think we have already talked about granular sludge in the anaerobic system. This is Hatze Lettencha, who actually perfected this anaerobic upflow system. And I think Professor McCarthy has just taken that a step further now. But we've seen the granular sludge here. We see the granular sludge in the Anammox bacteria. And now, with the development in Holland of the aerobic sludge, you can see these aerobic granules forming, and quite different from what we are used to in terms of activated sludge. So what you've seen in some of those pictures I've shown you, I think, is something like this. When you start getting a very high F to M ratio, you seem to get these granules forming, but out of the granules you grow filaments. And that is, I think, what those clusters are that we've seen there. So what the Dutch developed, and especially Professor Mark van Lustrecht, is to actually get enough shear in there so that those filaments keep shearing off. And you end up with a granule, and what you end up doing is, well, this would be a normal activated sludge flock, and this is a a sketch that Professor Mari Winkler made. She's from the University of Washington. And here you see how the organisms arrange themselves in a flock. But the time you start forming a granule like this, there's obviously going to be an oxygen gradient through there. And when you have the oxygen gradient, the nitrifiers will arrange themselves on the outside of the flock. And then the denitrifiers, because of the high F to M ratio, you also have a food gradient in there. And so they get some food and they can get denitrification happening immediately. And as a surplus, and I must say this is just about the same way I discovered biological phosphorus removal, is that it was a pure accident. I did a few things right without knowing what I was doing. And so here again, inside the flock gets totally anaerobic. And what we see here, somewhere around there, the PAOs arrange themselves. So now we can do all of what we did in an ordinary BNR in different zones. We can do it within the same flock. And we get simultaneous nitrification, denitrification, and phosphorus removal. Sorry, where was I? Oh, yeah. So the process that was developed, they call it the Nereda process in Holland, is basically works on the same way that SBR that I just demonstrated to you, in that they feed during decant. But whereas I fed only on the one side and decanted on the other, what they do is feed over the whole surface area at the bottom. And these were the granules here, and the upflow velocity through the granules, you get a very high F to M ratio here, and they waste the sludge from the surface here. So the lighter sludge gets wasted, and it so happens the GAOs, or glycogen accumulating organisms, also arrange themselves to the top here. So preferentially you waste them out there. And as you feed, you decant, so the clean water is decanted to the top. Normally these tanks are like 20 foot deep, and you actually displace the clean water all the way up. So what you get then is a cycle, and that feed and decant period happens at the same time. And when you stop feeding, when that liquid level gets closer to the top, you start aeration. And normally there are 3 tanks, but the aeration process actually carries on into this phase, and then the settling time is only 20 minutes because the sludge settles so very fast. It settles for 20 minutes and you start feeding again. And here you see, this is on a sieve, the granules there. We'll see more pictures of that. And that is the even distribution is very necessary. Otherwise, you really need to replace that clear liquid fairly, how can I say, on a more sustained basis. Now here you see the very first plant they built was in a little town called Gansbaai in South Africa, and this was what was remarkable about this plant. It was actually treating septage. Now, one of the first things that I would be concerned about is, bulking sludge. We have seen when you have very different, how can I say, loadings on it, great variation, you see bulking of this. But look at this plant here, because it's mostly septage that it's treating. The COD in range from 800 to 10,000 milligram per liter, and the coming out at 100. Now that 100 means that the VOD was probably less than 5. The total nitrogen going in at 150 to 200 comes out less than 10, and the phosphorus less than 1. And I visited that plant, and I've taken a picture, and in 3 minutes, that's how this settled. 3 minutes down there. And here you can actually see on this here the granules. And I should have pointed over there too, but I cannot see that one very well. And so there you see some of the granules on this guy's finger. I also visited the first plant that they built in the Netherlands. This is they call this APA. And these have 3 tanks. And again, remember, there are no moving parts inside the tanks. It's just the upflow. And at this point, I think this is before it starts because it's not really up to the level there yet. When the clean water flows over into the launder. But what was remarkable about this plant is that they have 30% of the load is from an abattoir or a slaughterhouse. And I have designed a number of plants for slaughterhouse wastes, and what I have done is put balancing in, because the slaughterhouse, there's a lot of blood coming down sometimes, and there's a lot of chemicals coming down. I never dreamed of not putting balancing in for treating that waste. But the waste comes in here without balancing. So it tremendous peaks in loads and so forth. And what you see, well, that is just I think this is a bit of a propaganda picture. Water is not that clear, but here you see the settlement of normal flux, probably, again, a very high SVI sludge, and that's the flux after about half an hour settling. But in this APA plant, what you see here is after filtration. Now, I must just say this one thing also. It takes a little while for this process to actually settle down. It may take 6 months. And during that 6 months, you get higher turbidity, and you get suspended solids maybe up to 20 milligram per liter. So they did put filtration in, but here you can see, and down here I want to show you that the TSS was 0.5, so that means they definitely had filtration on this plant. But just look at the removals here. The COD got down from 879 to 27, and 97% removal, TKN removal, and the total phosphorus less than 0.3, coming in at about 9.3. So I think this is absolutely remarkable. And here is another plant that I visited. It's called Garmerwolde in the Netherlands. And what you see here is they extended this plant, and they needed to increase the capacity by 40%, so they built these Nereda tanks, what they call Nereda, the process here, and that was supposed to treat 40%, but right now it's treating 50%. They found it's working so well that they're treating 50% of the flow in here, and the rest is treated in that plant. Here is just a number of references of the plants, and as you can see, even this Garmerwolde plant is only about a 5 or 6 MGD plant, but they are now getting down to Utrecht in Holland, where it is getting to something like a 20 MGD plant. And what I think that's about the biggest that you would build anyway. So if you build a bigger plant, it would just be more of the same units. But the other advantage that they have is because of the granules, they can actually take very high peak flows. Up to about 2.5 times the influent flow can go through the plant without upsetting it. Now, I just wanted to show, when I visit this plant, I haven't been on a bicycle for 40 years, I think, but a very sustainable transport there. It's the only way I could get around. I took some pictures of the sludge, and you could just take it out here and draw it and pour it off like that, and you can see what happens here, how the granules stay behind there. So I just want to mention then that we looked at this for a plant in Kansas City, and we did some pilot plant work, and what we were looking at, that the footprint was there, was very important because the plant is in the floodplain, and we needed to get the footprint as small as possible. Very high rate of peak to average flow, and so we considered a number of processes, and the one that we eventually we considered this and did some pilot plant work, but eventually selected IFAS plant. Now here, I just wanted to show, it was very easy in the lab to get these granules and to form these granules in here. And we got it to the point where it nitrified and almost totally denitrified. But the problem is here of scale, and you need a certain amount of shear, but at the same time you cannot over-aerate it. And when you over-aerate it, you have the problem that you don't get that gradient in the flock to do the nitrification and the denitrification. Now here you can see in this plant we were already starting to form the granules, and there was still a little bit of the fluff around it, and then we had to stop that process. So in the interest of time, I just wanted to make a quick summary here, and I say that the granular activated sludge is a product of selecting for organisms that form, it's a selecting process for the organisms that form granules, so you wash out all the others. When you start off, you start washing out the others, and you end up with just the membrane, with all the granules. It's by now a proven technology, and they're already building about 25 plants are almost completed, and a very simple process to design and operate. There's no moving parts inside the tanks, so maintenance is very easy. And because there's no recycle pumps, no mixers, and so forth, the lower energy, and you get simultaneous nitrification, denitrification, is energy cost is about 60 to 70% of a BNR, and I say a well-designed BNR plant, because some BNR plants, there's a lot of over-mixing taking place, and so this energy could almost be less than half. The footprint is about 40% or lower than that of activated sludge plant, and I think this is what is in favor of this type of process, because we see more and more the pressure on getting more treatment in very small areas. And the results so far show that it's a very stable process, but I still feel that one would need to do a small pilot plant to just make sure that it's going to work in your specific conditions. One of the things that we sort of suspect is that you do need some volatile fatty acids. So in the lab unit that we did, we actually took some of that sludge and fermented it before we sent it through, and that seemed to have helped with it. So thank you very much for your attendance.
Thank you for an excellent talk. We have time for a couple of questions from the audience.
A really interesting talk, thank you. I wanted to ask you, in the traditional BNR processes, it seems that there are a lot of design and control issues that one needs to worry about to make sure everything functions properly. What are the important things here other than just this first step of selecting the organisms?
Yeah, well,
what's important in terms of making it succeed?
Right now, this the sort of experience, the know-how is with the Dutch company of DHV, and they are very secretive about exactly what it is that they do.
I've had conversations, I know.
I visited some of the plants, but many of these plants are running remotely. The one in South Africa, there's nobody there. Even though it's septage that they deal with, there's nobody there. It runs by itself. There's nothing much that you can do anyway inside the tank. So it's all in the design and the technique and the know-how on how to arrange those things so that you can make sure, and the control system, which is also a proprietary system at this stage, and so to get the right amount of shear in there, and to get the DO to the level where you're not over-aerating and obviously not under-aerating also. So that is the know-how that is still proprietary, that we don't know exactly yet. But what I've seen, it is so easy to form these organisms, granular organisms, but the technology to sustain them, that is what we need to know. So what we looked at when we tried to use this technology is actually to work with the Dutch people on that so that we could get their know-how on this.
Well, will they guarantee it? I mean,
Yes.
if they will, okay.
They will guarantee that.
Other questions?
Yeah, so, Bruce, over here.
Oh.
You can't.
Got a light in my face.
So,
Oh, there.
it's okay, you don't have to see me. Just quickly, in terms of startup, does it make any sense to take an existing reactor and transport over some of the solids?
Yes. I may just add that they have done startups in various ways. You can start from scratch. It takes a little while for it to develop.
Yeah.
And to wash out the organisms, or you can just buy it, and that's what they now do because they've got plants that produce the granules,
Right.
and they simply take a tanker and take it there, and within a week it starts up.
That's what I thought.
It's
Okay.
very,
Yeah.
very fast
Yeah.
once you got the granules.
And in terms of solids, in the anaerobic digester, any?
Yeah, well, the sludge is not that different from normal sludge that you waste. It's because you're wasting from the top, you're wasting the lighter sludge. And it gets up to, so far they haven't seen a great difference between that and normal activated sludge to the degree that you have to thicken it up
Yeah.
for digestion and so forth.
Okay, thanks.
Other questions? Just a quick one. I was curious, do you see many plants converting to aerobic granular sludge processes?
I think that especially where footprint is an issue, we were just talking about Sacramento, for instance, where although I knew about this technology, we put in a standard design. The point is we had the clarifiers, the primary clarifiers were there, the secondary clarifiers were there, land is available, so there was no reason to really push for a small footprint. But certainly I can see that many people are getting interested in this because of the footprint and the low energy, because the energy cost is coming down now. The energy cost for a normal activated BNR plant, a well-designed one, can be in the order of 25 to say 30 kilowatt hours per person per year. Mm-hmm. And they now bring it down to below 20. Now, if you then take the digested sludge and you digest the sludge and you get some energy back, the total energy is already dropping to quite low figures for the plant.
All right, well, with that, let's thank Dr. Barnard for an excellent talk.